let's do a small recap first. So most of these lectures, at least for now, we will actually focus on how do you create a large language model. Okay. So create your own LLM. Okay. So that's kind of the focus that I'm going about right now, because the courses that you are registering to are actually use cases. So I would say that so fine-tuning, so the fine-tuning course basically in the agents course are all you have to use a LLM. You have to use a LLM. So at the end, you definitely have to use an LLM. So any course is you need to take an LLM, and then you can use your fine-tuning model or your agents course model. Everything needs to have that LLM. So why not create your own LLM? So what is one of the challenge that you guys think if you are trying to run your LLM on your machine? Look.
The token part.
GPT-like architecture. Sorry.
The token
So
part.
let's say you have created. Sorry, can you come again? I couldn't hear you.
Usually the tokens, if we don't know how to use it, then we like suffer like doing it.
Tokens, you can, if you are creating your own LLM, you can have, so if you have your own LLM, you can also mention your own token. So we will actually talk about how to create your own token event. Okay, so you can try to have that own token. So if let's say this is my LLM, so this is my Danny LLM, for example. So I can specify how my model can work. Okay. So that is also not a challenge, which, so all these models, for example, Llama, or what is that, Anthropic Claude, for example. So Claude, they will have their own way of tokenization, right? That's true. But so the way they will tokenize a sentence, that will be different. So they have their own chat template, kind of, right? So they have their chat template, and you have to use a tokenizer from Hugging Face and use their chat template along with the tokenizer. But even if you are, even if that, so this can be still solved. But one of the challenges always remain is your problem of GPU, right? So in Olab, you get a free version of T4, and I think the other one, Kaggle. Do anyone remember what Kaggle provides? The
T400.
free
T400.
T400,
T400.
yeah, T400, yeah. So it provides T400, but the problem is the GPU memory, right? So your GPU, these ones are around, I think, how much is that? Hang on. Let's just open a Colab notebook. Okay, learn more. Anyway, I think it's, let's think of it as 15 GB as a memory space or RAM memory. I'm not very sure, but probably that's the value. So so anyway, so this one definitely cannot. So when you are trying to train your model, GPUs always become a very difficult challenge. So so that's the reason, because your models are huge. So all these transformers that we were designing earlier, so today we will learn, many of you might already know that we use basically, uh, this is called multi-head, right? So multi-head transformers are a lot of transformers that are parallelly running on your GPU. So if you have all these problems, so a memory constraint is always there. Okay, so it's the GPU memory constraint, and you use kind of the multi-head. So there are many ways, but if I am because right now we are fixated to train a very simple model, so which is BERT, for example, or T5 multi-head. So multi-head attention is there in most of these language models. And here you have access to, so these runs parallel in many GPUs. Parallel to, so this runs parallelly in your GPUs, right? So that's one of the reasons you need a lot of memory space to process your training data, as well as your as well as running all these GPU data, right? So the basic model that was given in the paper had like 8. So this was 8 multi-head GPU, sorry, multi-head attention in the 2018 paper. So I will post this paper. It's probably most of you probably have heard of it if you have heard of attention. But this paper used 8 multi-head GPUs. But since then, these multi-head attentions have definitely increased a lot. Okay. So yeah, we'll discuss about it actually today. So this is kind of the topic of interest that we will have today. So so that's the one of the biggest constraint, that you cannot train it locally. You definitely need a GPU, and so there are options. Definitely, you have to pay, but there is something called RunPod. I'm not sure if you guys have heard of it. So it's called RunPod, and I'm not sure if I can log in here right now. Yeah, let's see. Yeah, so here you can crank up a GPU of your own. So there are different pods. So you can create and deploy a pod of your own. Don't have a pod right now because otherwise I'll get charged. So so you do have to have some explore. Let's see if we can fit in on explore. No, pods. So you can deploy a pod. So these are all the different pods that you can have. So see, these are some of the pods which have very high GB VRAM space. Okay, so this is what is the most important part that is needed for these kind of huge LLM model training, right? So so that is basically my ultimate goal to mention here, is that you need this kind of RAM space, right? So you finally probably cannot train your own model in a small T4 kind of GPU, right? So at least 48 GB of VRAMs are all needed. However, I haven't tested Gemma, which came out, I think, 12th of March, and they mentioned that you can have it on a single GPU. So most of this model run on multi-GPU, right? As you can imagine, this is a lot of VRAM space that is needed. So most of the models have to run on that, but this Gemma, which I will test sometime later, is can actually go into one GPU space. So now it's the focus is more going into smaller models, right? Which will need smaller, like with more better architecture, and then which will need small GPUs, so anyone can train their own LLM. That's kind of the focus going on. Okay, So yeah, so this is where most of these kind of model training can happen. But anyway, so let's go back and let me. See. Okay, so so let's just do a small quick recap. So we have encoder and decoder architecture that we had like a. So you have an encoder, right? So this is encoder and this is decoder. Okay, decoder. Okay, so what is encoder architecture? So they are mostly used for classification problems. Okay, so they provide context. So from your word embedding and positional embedding, they provide you context embeddings, and they are classification. Okay, so they are used for classification problems. And these ones are the ones that are used for your generative purpose. Okay, so this is the generative part of it. So all the generative models that you actually look at are basically these ones. So what is generative? So this is generative. So decoder, so GPT, for example, let's take the GPT-2, which is the first kind of architecture that was used. So GPT-2, for example, is a decoder model because it can generate new token. Okay, right. So what happens in the new token kind of architecture? So anyone remember? So let's say
Like uh, how does it handle and generate the text?
how it handles what? Sorry. Um,
The the way of handling and generating the text.
yeah. So the thing is that so it so when you have a sentence, so let's take that sentence I was using. Pizza came out of oven and it tasted tasted good. Okay. So what the language model has to understand is which it is this referring to. So is it pizza or is it oven? So we can understand that this is pizza, right? Because it tasted good. But the language the language model have to understand that where is it related to, right? So that's the reason what we do is we figure out self-attention. So how similar is the word pizza with came out? So how similar is pizza with the word came? How much similarity do pizza have with the word out, off, and then say oven? Like so, we keep calculating the word pizza. So this is a self attention. So we calculate the self attention score. So we actually train our model to improve these self attention scores with time. Okay. So these are the self-attention scores that pizza came out of the oven. So pizza is related to all these words. Tasted, good. So all these, so pizza is related to each and every word. So that's the self-attention scores. So if pizza has a very high kind of similarity with it, so let's say it has a very high similarity of 0.9, so 90%, let's say. So there's a high chance that it is referring to pizza than it is referring to oven, maybe 0.09. Let's say. Okay. So for oven, it has a similarity with or attention score of 0.09. The 0.09 is the percentage, or let's say 9 is the percentage that is contributing to it. So what you have to understand is the word it is actually has a dependency on all the other words. So in a mathematical term, if this is very crude way of writing it. So this is definitely just for an understanding purpose. Don't code it like this. Okay, never code it like this. So let's say we pick the word it, and then we say that because my it is very similar to the word pizza, so 0.9 of pizza. Okay, so it's very similar to pizza. So pizza contributes 0.9% to the word it. Then let's say came contribute, let's say 0.1%. Okay, or 1%. Out maybe 0.01%. Okay. So my word it at the end is also kind of a combination of all the other words that is present in my sentence. Okay, and then finally let's say oven. Okay, so with oven it might have a 0.02 or 2%, right? So very less. So what these numbers kind of give you, or these values kind of give you, is an estimate that then with these values you kind of get an estimate that it might be highly related to pizza or have a very high similarity of pizza than with oven. Okay, so this is how your language model kind of tries to figure out the context, right? So this is so when you give the context, you give these weight matrices, and then with my as my training model progresses, the words that are very much or more similar to the word that I'm trying to figure out here will get a higher score than the words that are not similar or could also become negative. Let's not forget about negative actually. Let's say very small percentage value. Okay, so this is called self-attention scores, and these are what we try to calculate for my encoder part. Okay, now let's go over here. Uh, oh. Now, what is the decoder part? So decoder is a generative model, right? So what, as I mentioned, your decoder. So decoder is a generative model. So what is generative? So predicts next token. So it predicts the next token. Okay, so if it predicts the next token, so let's take that sentence again. So let's say it. So I'm trying to again figure out it, and we are trying to complete the sentence now. So it has to complete with tested good, right? So anyway, let me put some color over here. Yeah. So this is what it has to predict. So it has to predict tested. So tested is the word that comes after it, right? So this is how it is because it's a generative model. So it has to predict the tested, right? So in this situation, what I cannot give my words is what my tokens cannot see, not my words actually. What my tokens cannot see is this part, right? So this is where it is masked. So you cannot, so it cannot have any kind of relation with tested or good for that matter. Good. So you cannot have any value over here because I'm trying to predict the next word, right? So that's one of the reason when I pick it and use it as a generative model. This is called mask attention. Okay. So I do not make a self-attention kind of similarity score, but I make it as mask attention score. Okay. And in a very, so we'll go over this a little bit more, but in a very layman term, we can actually say that, let's do a small matrix. So, 3 by 3 matrix, for example. So here is my word pizza. Okay. Pizza is awesome. So that's my pizza is awesome. Okay. And then pizza, this is again pizza is awesome. Okay. So pizza can see, so if I'm picking the word pizza, so pizza will have a self similarity with itself. So we can have something here. So this is this. So we are basically trying to create a lower triangular matrix. Okay. So is can see pizza and is. So there is a value over here. And then finally, awesome. Awesome can also check pizza is an awesome. So it can have access to all these 3 tokens. Okay. So finally, this kind of becomes my masking, the mask matrix, which I need to add so that I can prevent my tokens to check the next token or to understand the next token. This is what they have to predict. Okay. So this is what I will be giving it as a training part, and it has to predict something. So it will finally give out few probabilities, and my maximum probability is what my generative model will predict for me, or it can also depend on the temperature. So we'll define temperature and everything later on. But for now, this is how you use your masked matrix. Okay. Okay, so I'm spending a lot of time here. So let me go over and try to show you the implementation and all. Okay, so yeah, so here, okay, so so as I mentioned, GPT-2, ChatGPT, it's a decoder-only model. So also notice that GPT-2 is the actual model, and then it became a instruct-based model, which is called the ChatGPT. Okay. So here you have this equation for attention, or this is a masked attention. So everything remains the same, softmax, very qt. So that's the transformed version of t. Sorry, k. Then it is then scaled with the dimension of the key value plus the m matrix, and then multiplied with the value matrix, right? So as I was mentioning, what you do usually is the aim matrix that you kind of define over here remains like can be defined like this. So 0, 0, 0, and these can go into infinity because when you are using a softmax, that kind of, so if you have zeros then and add it to the matrix, it doesn't modify the matrix anything over there. But what happens is when you add infinity, so everything turns into infinity, right? My negative infinity. So the softmax of negative infinity then becomes 0, and that way you can avoid your token to see the next token, right? So that's kind of the goal of how you can use your masked attention, right? Okay, so add zeros to values we want to include and infinity to mask out. So that's kind of what you can have at the end and the stuff. And then if you are doing a softmax, or if you use a softmax over this matrix, so what happens is these become 0, in negative infinities become 0, and other ones get a value. So what happens here is pizza has 100% similarity to pizza and 0% to any 0% to others. Is has 0% similarity to awesome. Awesome have 90% similarity to awesome, 3% similarity to is, and so on. So, but it cannot. Awesome can see all the tokens before it, but pizza cannot. Right? So, and then you finally everything remains the same, so you get the softmax matrix, and then you multiply it with the value matrix, and that gives you the masked self-attention scores. Okay, so now it kind of over there, so now let's try to code it. So if my class is masked attention, NN module. So what is NN module? Anyone remembers? Anyone remember those NN module? So this is where you use it. Yeah, go ahead. Yeah, so it's the NN, so it's the neural network or NN, yeah, from the torch. So this is the neural network, what do I say? A library from torch, okay. Or the class, not library, it's the class, the neural network class from torch. Sorry. Where was it? Where was it? Yeah, okay. Yeah. So the neural network module, so we are including the neural network class from the from torch. Now this is my what do I say, the init or the constructor part of it. So this remains the same. If you remember from the last class when we were trying to use the self attention, so self then D module, D model. So D model is basically the my embedding dimension, right? So what was the embedding dimension? Let's look at this image quickly. I have it below. Yeah. So no. Yeah. So each and every word is represented by two vectors or two values. So a vector has two elements in it. If I can show you. Yeah, so basically each and every word kind of is represented by two values over here. So D equals to D model equals to 2. That's what it is mentioning about. But this is only for our purpose. 2 is never how it is encoded. It will generally a dimension of 1048. Sorry, 2048, 1024, 2048. So it's a very high dimensional problem, high dimensional encoding. Okay. Then you have two row and dimension columns. So this will these columns are again continuous parameters that we are using to modify our. So if you have a batch, for example, if you want to use a batch kind of, you have to use actually when you're training a model, you have to use a batch data. So you use all these values over there. Okay. So then finally, I define my so I define my query. So this is my, oh, that's the forward part. Okay, so here you actually kind of again going back over to self attention. Yeah, so this part remains the same. Yeah, so this part is almost remains the same for my math. So this is how I define my weight matrix for query, weight matrix for key, weight matrix for value. And this is an NN linear, which is basically a 2 by 2 matrix that we are trying to uh, figure out. And yeah, or try to initialize basically. So, and then we save the column dimension and row dimension, whatever it is, over here, because we're going to use it in the forward method. Okay. Okay. So then this is my forward method. Now here I'm trying to calculate the query key and value. So remember that's my equation, right? Query key. So take a similarity between query and key, and then we have to scale it up with the dimension of dk, right? At the same time, we also have to include this math. So let's look at this forward. So q equals to self, and then pass it through the weight or multiply it basically with the weight value or the weight matrix of query, weight matrix of key, and weight matrix of value. And then we calculate the similarity. So basically do a torch multiplication of q and k transpose at dimension of self row. That's the way to write it. And so this part is complete. Right? Now, if there is a masking, if you have a mask value, if mask is yes, or let's say if mask is not none, then we have to fill out the mask or we have to add the mask. So how can we think of the mask? So as I was mentioning, so these are all false, right? Or these so here it's just a truth table we can figure out. So if it is 0, then this is masked. Otherwise, if it's not masked, then it's false. Okay, over here. So the truth corresponds to attention value that we want to mask out. So when there is a true value, of course, this corresponds to the attention that we don't want, right? So in your torch, you can use masked fill. Yeah, so masked fill, just check out masked fill sometime, or whenever you're coding. So masked fill and put this, so pass the mask and then the values. So what will be the value where we are masking it? So put a very low negative number. So 1 to the power minus, or sorry, a very low negative number in the sense this could be a very high value, but it has to have a very negative value. So it can be e to the power 20 or anything very high with a negative value in front. Okay, so that kind of becomes your 0, goes to 0. Basically, we can think of it going to 0. Okay, so that is kind of the tensor that is generated for us, and then we have calculated this mask, and scale similarity is mask fill, and then the same way we now calculate the attention percentage, scale similarities, and then attention score. So we run the scale similarity to softmax to determine the percentage of influence that each token should have on one another. So that's the same thing that I was mentioning about, is how this thing, how your pizza, for example, here, so how it or this token is being affected by all other tokens. So that's the kind of the softmax is kind of calculating for us. So that's the percentage of that is determining. So this part of it is determining how much is the influence from others, and that's the multiplied with value. Okay, so let's go on to the implementation now. So I provided this in the GitHub. So please check from the GitHub. And here here you are initializing all this WQ, WK, WV, and row, columns, and etc. Then I define the forward, okay, and forward takes a token encoding. What is this token encoding? So we get this token encoding from our these values, right? So no, not this one. So each and every word have a it's been defined with embedding, right? Word embedding, then positional embedding. So this is what we are using. So these are our token embeddings, right? Okay, and if mask is not none, then we use the scale similarity and fill it out with mask. So as I was mentioning, you can have any high numbers, okay? You can have very high numbers over here. Then calculate the attention percentages, attention scores, and then return the attention scores. So if you just run this, uh, so how do you pass the mask? So mask is basically using a torch.trill. So torch.trill, which is torch.trill, it returns you this lower triangular part of the matrix. So if you have a matrix like this, a torch matrix like this, and then you pass it to torch.trill, all these ones become 0. So the upper part becomes 0 and the lower part remains, right? So that's what is happening is we are creating a torch trill, okay? So ones are what is that? So each and every value is 1 except those 3 values at the top, right? So we pass this mask to the forward method, right? To our forward method, token embeddings and mask, and then it calculates the similarity score for us. Okay, so that's kind of the similarity score that we are getting out. So that's returning the similarity score. And you can also make a individual prediction like this, which I'm not following, but you can also make these individual predictions and check if finally once it goes over all of these values, it returns back those numbers. Right? So if it is returning back those numbers. So yeah, please check this and try to understand a little bit yourself. And that's kind of, yeah, check this individual scores also. Okay, so that's how we have your masked attention. Now, so again, let's go back to, so this is how you calculate your self-attention and your masked attention, right? So when, so now going back, when we first started, or when the attention is all you need paper came out, actually. So this is the paper that which came out in 2017, I think. Yeah, I think it was first published in 2017. Yes. So here they used a encoder-decoder structure because, or encoder-decoder architecture, because they were trying to figure out the relation, because they were trying to figure out the relation between, or not relation, they were actually trying to do a machine translation. So machine translation is English to French, and from like translating between different languages, right? So that needs an encoder and decoder architecture. So it needs a connection between the encoder and decoder architecture. So what is an encoder architecture? What do you have in an encoder architecture? So what type of transformers, what type of attention does these encoder architectures use?
Self, self.
Self, right? And the ones that and what type of architecture does these
Mask,
ones use?
mask,
The decoder?
mask,
Masked,
mask.
right? So masked, right? So here So they just remember these two things: self for encoder and max for the decoder. Okay, so the decoder and the encoders are connected to each other with encoder-decoder attention. So the encoder-decoder attention uses the output from the this attention. What is this attention? Because this was used for your machine translation purpose. So it uses the output from encoder to calculate the keys and values, and queries are calculated from the output of masked self-attention generated by the decoder. Okay, so this is how they try to calculate over here. So it's very high level. Even if you don't understand, it definitely needs some more looking into the code, how it is done. So next class onwards, we will try to first go over an encoder architecture, which is used for a classification purpose, and then we will look into more of the decoder part of it. Okay. But this or not, but actually, let's say the encoder-decoder attention is also called cross attention, and it's not very much used for machine translation these days anymore. But or I mean, there are many other purposes that the self-attention or the masked attention became very popular. Okay. But these days, you probably have heard of multimodal models. So what are multimodal models? So multimodal models, so let's say you are providing image sequence or a sound sequence or a music sequence, probably to the encoder part, and you are asking the decoder part to generate an caption for this. Okay, so this is where your encoder-decoder architecture or encoder-decoder attention still works. Okay. Okay. Yeah, so now, so the final part of it, let's discuss. So this is called, this part is called this multi-attention, multi-head attention. So that's called the multi-head attention. Okay, so the basic, um, the or let's look at the architecture first. So instead of only having one head, so each and every unit like this is basically which gives out a contextual embedding at the end can be thought of as a head. Okay, so we call this as a head. Okay, so when we have multiple heads calculating attention, it's called multi-head attention. Okay, so these are each and every one of these are called as head. And why do you need this? Because our what do you say? Mm, our paragraphs or our text is much more complicated than only a single sentence, right? So it's very so it's extremely essential that we do parallel processing in the GPUs. Okay, so why this kind of also why attention architecture became very famous is because you can parallelly compute all these matrix calculations on your GPU. So that's the reason it became very popular. Okay, and it's still being very widely used for any of these language models. So that's what I was mentioning, that when your paragraphs or your sentences become very complicated, you need to have multiple times or multiple key query and values coming out of these attention models or self-attention models, or and then trying to how do you say trying to make more sense out, or get more context out of your sentences. Okay, so anyway, I think you get the concept that each of these are called heads and you can have multiple heads. So original paper had 8 heads, but now there are many heads that these models are using. Okay, so now if you have all these heads, then how do you club everything together, because at the end of it, you need to get sum total of all the values that are actually coming out of each and every head, right? So what you do is you connect everything to a fully connected layer. So if you remember the perceptron class I was taking, so at the end of it, you have a fully connected layer. So what happens is the hidden layers are fully connected to the output layer. So all of these nodes are connected to the output value. So the contextual value that is giving out, right? So it's a fully connected layer. So at the end, you need to attach a fully connected layer that will give out your context. Okay. So this is how your multi-head attention kind of works. But there are few different ways. So if you now imagine that here my encoded value was only 2 dimensions. So I had pizza was encoded as 0.1 and 2.13, right? And I have a value. So the weight matrix for the values is also has 2 columns, because this was 2. So we had to have a 2 column. But imagine if you had something like this. So imagine when my pizza have a very large value, right? So my billions and billions parameters, how do this come into picture, right? Because these models have billions and billions of parameters, right? So if I have, and then n, and n is 20 9 2048. So 2048, right? So n is 2048. So that means it's a dimension of 2048, and your weight matrix, so weight is also 2048 cross 2048, right? 2048. So you can imagine if I have 100 of this, so how many parameters, trainable parameters does it become? So it's a huge number, right? It probably will hit 1 million, definitely. So that way, going into a billion parameters is not uncommon, right? If you have huge word embeddings, and then because what are you training? You are actually training your weights, right? So you are updating your weights at every training step. So if you have this number of multi-head attention, so hitting those number of trainable parameters can definitely shoot up a little bit, quite fast, right? So there are many techniques where you can actually try to kind of squeeze these numbers. Okay, so you can probably reduce the number of outputs by modifying the shape of the value weight matrix, which is not the best practice, I would say. So if you have, instead of 2, if you have 1, you can have a value with 1, but not the best practice, in my opinion. In this example, yeah. And yeah, so one of these example is actually reducing the values, but we don't want to do that probably. Or we can also reduce the values, and each head has one output if you reduce the weight value, and or the number of columns. Yeah, we can reduce the number of columns, and then it will give only one value, and that could lead to more and that can give only one value over here instead of 2, and you can have a fully connected layer over it. Okay, but it's okay, this is one technique, but I wouldn't say this is the best one right now. But for this purpose, for our simple LLM that we want to train at the end, we can still keep this kind of technique. However, there are very much more advanced ones, which we will probably not cover right now. Okay. Okay. So, any questions on this? This PDF is available on your GitHub. Okay. So the AI Weekend project, that PDF is available. This is also available, and next week we'll start more coding, some more coding on this. Okay. Any questions?
Ma'am, could you just tell the basic difference between must attention and a multi-head attention?
So multi-head attention is so marked attention and multi-heads are repetition. So multi-head
Oh, okay.
can be,
Okay.
yeah, so it's a repeated, right? So
Mm,
this is repetition, right? So this is how one of your attention will look like, be it a must or a self. Okay. So this is your building block of one of your attention models. So this is positional, this is word embedding. When you have a multi-head, so these are repeated. So all these blocks are repeated. So this block is repeated, this is repeated, and this is repeated. Okay. So this can be repeated any number of times you want. So we'll do the coding next week on multi-head attention, and that will make it a little bit better. Okay.
sure,
Okay.
thank you.
Yeah. So just the last thing. So we have been discussing a lot about LLMs theoretically, also doing some exercises, but you have to also remember that you need to deploy your models, right? So even for your language model tuning, why are you tuning those? Because you need to create some applications out of it. You need to create app which people can use, right? So and then you have to deploy those apps. So deployment, so model creation, creating a model and deploying the model is equally important. Also, that along with your increasing your knowledge in these theoretical areas or training the model, right? So one of the things that I wanted to touch base was Docker. Okay. So I'm not sure how many of you are actively using Docker, but if you are on your, so Docker, I'll give a very high level. Maybe I don't have too much time for today, but next few classes we'll talk about Docker a little bit more. So in a very high level, when you are, let's say you are trying to deploy your application. So what you have to do is for different systems, if it's on a Windows, if it's on your OS, Mac OS, or if it's on Linux, right? You have to have different installation processes. So brew, pip, things like that. You have to go about and doing it on your Windows exe, right? So that becomes very cumbersome, right? So it always, if you are trying to deploy your application, it becomes very dependent on your OS, right, at the back, right? So and you cannot take that same application and deploy it elsewhere. So or you can take it definitely, but it's a very too many steps. You can go wrong somewhere, right? So that's why we containerize our applications. So we isolate the environment. So you can actually say that fine, we can also crank up a VM, a virtual machine, and you can isolate the environment that way. But the basic difference lies over here is, so you can have a Docker kernel running over here. So this is your physical machine. This is your host OS. And this Docker kernel or Docker is actually based out of Linux. So even if your Docker is actually running on your Windows machine or your Mac OS, it is still it's still running it's still running the Linux at the back of it. Okay, so it has a Docker container over here. So this is the problem with VM, is you still need to have a guest OS, which can be avoided in Docker. So once you're running this in Linux, you can keep your application. So you can keep deploying a lot of applications on this Docker kernel. Okay, so that's one of the reason Dockerization have become very popular these days. So there's Dockerization, there's Kubernetes. We'll not go into Kubernetes, but we'll more stick to Docker. Okay, so for next week, I want you guys, if you have time, to install Docker and run few comments. So I just gave a small video lecture on or just video steps, okay, to how to run your, so how to install your Docker and then run few of these comments, okay, and then you can actually realize that how Docker is working. So to give you an perspective, a quick perspective, let me show you how I can run. Let's say I have most of you know how to write a Node.js application, or even if you don't know, that's fine. So let's say I have a Node.js application like this, okay? So very simple Node.js application, which can locally run on my server, server port 3000, okay? So I'm running 3000. But if I want to make it containerized, I can actually put it onto Docker and then run it. So for that purpose, so let's say my Docker right now is running actually. So here, so I can either, let's put this. So I can run this on localhost directly, or you can Dockerize this application. Okay. Oh, what happened? Okay. Anyways, okay. Let me show you the Dockerized part of it. Actually, so we can run it here, or let's just go over here and show you that I have used it on my Docker. So I'm running it on my Docker in port 3000. I have to give some more information on Docker. It's just an example right now to begin with. So let's open this on my local host. And here you can, oh, that's not the one. Let's open this one. So here, this is my Docker, which is connected to my local host 3000, and you can now run my Node.js app over here. So ultimately, it's not running directly on my system, so it's not dependent on my OS, and you can run it on your Docker application. Okay, so I created an app and created an image Node app, and then it's running over here. Okay.
Hey everyone, welcome to this data science problem solving session. Here we are going to understand a valid Sudoku using a HashSet. So whether you solve Sudoku or not, it doesn't matter. It's just the way of solving this problem with HashSet that you can detect for duplicate values in a structured way. So let's read the problem. Determine if a 9 cross 9 Sudoku board is valid. Only the fill cells need to be validated according to the following rules. Each row must contain the digit 1 to 9 without duplication. Each column must contain the digit 1 to 9 without duplication. And each of the 9 figured three sub-boxes of the grid must contain the digit 1 to 9 without duplication. And a note, Sudoku board partially filled should be a valid but not necessarily the solvable board. Only the fill cells need to be validated according to the mentioned rules. So, what does the first rule mention? Each row must contain the digit 1 to 9. So, what is my row? The digit 9. Right? So, each of these 9 rows should have digit 1 to 9 without repetition. Then each of this column should also have 1 to 9 without repetition. And then each of the 9 by 3 by 3 grid. So it would be 9 grids. So these are 3 by 3. So it can only have one value, like this one over here, 6, but then it also cannot be repeated. Now what does this node say? So it has to be partial cells. So these are partially filled code, and it's not necessarily solvable. So what do you mean by necessarily solvable? It's because so here notice 1, 2, 3, 4. So here let's have 1, 2, 3, 4, 5, 6, 7, 8. And then 3, 4, 5, 6, 7, 8, 9. And this Sudoku actually is not solvable, so it's not valid. Because if I want to put a number over here at the last cell, what do you have to put? Because if I put 9, then this row is solvable. But at the same time, this becomes a repetition over here. So we already have a 9, right? So that's the reason that if I put a 1, which is not present in this column, this is a repetition over here. So this is not a valid solution, it's not solvable, but for this purpose, for this coding exercise, this is also a solvable part. So we should also consider this example also, because we are not solving the suitable answers, we are just trying to see if there is duplicate. So in this, so what we are going to do is use the concept of HashSet. So what is HashSet? So this concept of HashSet is to check if there is any duplicate or not for each of these three conditions. Okay, so we're going to check that HashSet thing. So the rows and columns are fine. So row can have we can have a HashSet. So HashSet HashSet for a row. Similarly, we can have a column HashSet. But how do you create a HashSet? Because these indexes are fine, it's good comparison, right? But how do you create a HashSet for this? So, so here, okay. So here, we can actually think of this as maybe just try to rename or re-index it. So re-indexing this value, let's say, here, here, 4, 5, 6, 7, 8, and similarly, 1, 2, 3. Okay. Now we can consider this 18, sorry, not 1881 cell, and so this is indicating the first, so this one, 2, 3, then so yes, 0, 0, 0, 1, and 0, 3, and then and use this as the second row. Right? Second row, 1, 0, 2, 0, 1, 1, then 1, 2, and here it is 2, 1, then this 2, 2. Okay. We can have a new re-index value of all these so these subsets of 3 by 3 can be now re-indexed into 0, 0, um, 1, 1, like 0, 1, things like that. So we can have a new set of kind of de-indexing values. So what happens if we have this? Then, for example, if we have 4 by 4, so something we try to check the 4. So over here, let's say. So we're trying to check, so we are going to re-index that one. So 4, comma 4 by 3 is the one. 4 by 6. Okay, this becomes 1, comma. So it's kind of the index. It is giving this. So this way, we can tell which of the 3 by 3 grid is the value is part of. Maybe we can fix it here. 8 by 8. Mhm. 8 by 8. 8 by 8. 6. So that's 3, 2, comma 6. It's part of this section. Okay, so it kind of gives you an idea. So we can tell actually which of the 3 by 3 gates is part of again. Okay? So then what happens to my key? So if I'm thinking of this as a key value problem. So the key, what we can write for the key is we are reassigning this row divided by 3 and columns by 3. So that kind of becomes my key. And value set within the set we can have the value as a hash set. So this is how we can iterate over these keys, and the hash set becomes a value to check for duplicity. Check duplicity. Okay. So I hope this kind of makes sense, and then we can probably go over to the coding part. By coding this, begin this. That, and then solution. Get here value. So we type the board. The board is a list of uh, so it's a list of strings and which is the variant. Yeah. So for I in range 9 and for J in range 9, so this is for the that we can have it for the rows and for the columns. But before that, to specify uh, rows equals to rows equals to um, probably use collection. Collection can default to set and then false equals to collection default gets set and then between set and then so it's use collection. And I forgot to mention, so it actually will take over the value of or what is it complexity. The complexity for this would be actually of 1 for each element, and that is 9 plus 1. So that's kind of the O of 1 for each element, which we might concept. Okay. So then we're moving back to our code, so that's row and column, going over row and column. And then here, the here if board. So if board is dot, so we can create a board and send some the blank values can be dot, and then if it's a dot, then we can continue. We can skip that one. Otherwise, um, otherwise if right, so if board ij um, in row I or board ij in row columns j. So we have defined rows and columns over here. Or board ij in square I mod of 3 j mod of 3. So this means it is actually repetition. So it is actually repetition. Then we need to return false. Right. Otherwise, we need to else we can have rows dot I add to the board ij add. So with the rows I comma j added, and then you add so because we are this is not repeated, so we just add the board values over here and return true. Right. That's kind of your okay. So we did use collections and we can getting an alert over there. So we can serve everything. There's using. So from typing import list and import column. So that is yeah. So that's it. So okay. So now we need to test the solution. Okay. So now we created the class solution with method is valid solution, and let's test this for this. I'm going to get the board value from the board here. Four, that's two. So next, let's make a modification of this. Here.